The wind crosses the Mongolian steppe with nothing to slow it. No forests break its path. No hills deflect its force. The temperature drops to 40 degrees below zero, then lower still. Wind chill drives the effective cold past 50 below. Exposed skin freezes in minutes. Metal shatters. Water turns to ice in seconds. In the middle of this frozen plateau, a white dome sits anchored to bare earth. Smoke rises from its center. Inside, a family sleeps in warmth. The structure is called a jair. Westerners call it a yurt, though that word actually refers to territory, not shelter. For 3,000 years, nomadic herders have lived in these portable homes through winters that kill unprotected humans in hours. The jair is not a tent. It is a machine for survival. Every component refined by disaster, every detail calibrated to resist a landscape that offers no natural refuge. The question is not whether the jair works. The question is how. How a circle of wood and wool creates tropical warmth when the world outside is trying to freeze everything solid. The steppe imposes brutal constraints. Temperatures regularly reach -40 Celsius. During extreme events, the thermometer falls to -50. The high altitude traps cold air over the plateau for months. The Siberian high-pressure system settles overhead, stabilizing the freeze. But temperature alone does not kill. The wind multiplies the cold. Without trees or terrain to break its flow, wind accelerates across open ground, creating laminar currents that hit structures with tremendous force. A rectangular building presents a flat face to this assault. Wind crashes against the wall, creating high pressure on one side and a dangerous vacuum on the other. The pressure difference generates lift and drag, forces capable of tearing conventional roofs from their anchors. The jair is cylindrical. Aerodynamic testing shows that circular structures reduce the drag coefficient by approximately 30% compared to rectangular structures. Wind does not crash against the jair. It flows around it. The conical roof, low to the ground, channels wind pressure downward rather than allowing it to create lift. The harder the wind blows, the more firmly the structure presses into the earth. This is not an accident. This is evolutionary design. The steppe tests every structure against 4 types of catastrophic winter disasters, each with a different name. Chaga'an Zud, the White Death. Heavy snow buries the landscape in layers that can reach waist-deep or higher. The weight accumulates on the conical roof, demanding vigilant clearing every few hours to prevent structural collapse. Snow isolates the jair completely, cutting off access to pastures and water sources. The family must create tunnels to access the livestock pens. The snowpack creates an insulating skirt around the base of the jair, but this protection comes at a cost. Accumulated snow blocks ventilation gaps, trapping smoke and carbon monoxide if the stove burns inefficiently. The herder must balance thermal insulation against the risk of suffocation. Kar Zud, the Black Death. This is extreme cold without snow. Temperatures plunge to -40 or below, but the sky remains clear and the ground bare. Without snow to melt, water sources freeze solid. Wells become inaccessible. The herders must hack through thick ice or melt what little snow accumulates in sheltered spots. The lack of a snow skirt leaves the jair's base exposed to wind scouring, which steals heat through the felt where it contacts frozen ground. Livestock, unable to paw through ice to reach grass, begin to starve. This type of dzud tests not the structure but the reserves: food, fuel, and animal fodder stored against an emergency. Tumor Dzud, the Iron Death. A false spring arrives. Temperatures rise above freezing for a day or two. Snow melts into slush. Then the cold crashes back, flash freezing everything into a landscape of glass. Ice coats the ground in an impenetrable shell. Horses cannot break through with their hooves. Sheep cannot paw down to the grass. The herds starve while standing on top of food they cannot access. The ice reflects moonlight and starlight with high albedo, increasing radiative cooling at night. The temperature inside the GR can drop faster than during normal cold because the Earth itself has become a mirror of frozen thermal loss. Kuiten Zud, the cold death. This is pure temperature anomaly. No snow, no ice storms. Just cold that drops far below historical norms, reaching -50 Celsius or colder. This tests the absolute thermal resistance of the felt and the occupant's metabolic reserves. At these temperatures, exposed flesh freezes in under 2 minutes. Breath crystallizes mid-air. Metal tools shatter if struck. The stove must burn constantly, consuming fuel at rates that can deplete winter stores. Families huddle together under piles of sheepskins, minimizing movement to conserve calories. This dzud reveals which jairs were constructed correctly and which cut corners on felt thickness or tension band tightness. These disasters once occurred every decade, giving herders time to rebuild livestock numbers and replenish stores between catastrophes. Climate change has compressed the cycle. Zud events now happen every 2 to 3 years, placing unprecedented stress on traditional survival systems. Yet the GR remains the most viable shelter because 3,000 years of evolutionary pressure designed it to handle exactly these conditions. The skeleton of the jair is wood. Not just any wood, willow, birch, or larch, chosen for flexibility under stress. The walls consist of collapsible lattice sections called khana. Each section is a grid of wooden strips pinned at their intersections, forming diamond-shaped openings that can expand or contract through a scissor mechanism. This is not decoration. This is load distribution geometry. When snow accumulates on the roof, weight presses down on dozens of roof poles that rest on the lattice walls. The diamond pattern transfers this vertical force efficiently to the ground without concentrating stress at any single point. The flexibility prevents catastrophic failure. In strong winds, the wall breathes and flexes rather than snapping. The strips are not joined with metal. At -50 Celsius, metal becomes brittle. Metal also conducts cold directly into the structure, creating thermal bridges that allow heat to escape. Instead, the Mongols use jair, strips of raw camel hide applied wet. As the hide dries, it shrinks, creating a grip tighter than any hand-tied knot. But unlike metal, dried hide retains elasticity. When the GR shudders in a blizzard, the hide joints absorb kinetic energy, allowing slight rotation without breaking. The structure responds dynamically, flexing rather than breaking. The roof poles slope from a central ring down to the top of the walls. Gravity pulls them down and out. Without restraint, this outward thrust would splay the walls flat. The solution is koshlon, heavy woven wool ropes that encircle the top perimeter of the lattice. These tension bands convert the roof's outward thrust into compressive hoop stress, tightening the wall sections together. The physics creates a feedback loop. More weight on the roof generates greater outward thrust, increasing the tension in the bands that clamp the walls more tightly. The structure automatically strengthens under the conditions that would destroy it. At the apex sits the tuno, the central wooden ring through which all roof poles pass. In smaller jairs, the ring is self-supporting, held aloft solely by the compression force of the poles. In larger structures, 2 vertical columns support it. The tuno must withstand immense pressure from dozens of converging poles. It is often steam-bent or mortised from heavy timber to resist splitting. But the tuno is not merely structural. It is the only opening in the entire building. It serves as a skylight and a chimney. It also functions as a timekeeping instrument. A practiced family can dismantle this entire system in 30 to 60 minutes. The lattice folds, the poles bundle, the felt rolls. Everything loads onto 2 or 3 camels or a single ox cart. In 1 to 2 hours, the GR stands again. This portability is not convenience. It is the ultimate insurance policy against disaster. The wooden frame provides shape and structure. It does not provide warmth. The insulation is felt, SGIU in Mongolian, a non-woven textile with thermodynamic properties that set it apart from any modern material. Felt is made from sheep wool. Wool fibers are covered in microscopic scales. Under heat, moisture, and mechanical agitation, these scales interlock, creating a dense mat that cannot be unraveled. Manufacturing felt on the steppe is a communal industrial process that involves the entire extended family and sometimes neighboring camps. Shearing happens in spring to harvest the dense winter undercoat that kept the sheep warm through the previous freeze. The wool is still greasy with lanolin, which helps the fibers slide and lock during felting. The loose wool is spread on the ground and carefully picked through to remove debris, including burrs, dirt, and dried dung. Then it is wetted with water, sometimes mixed with whey or fermented milk, to serve as a binding agent. The wet wool is rolled tightly around a wooden pole, creating a cylinder as thick as a human torso. The new wool is wrapped in an old piece of felt, the mother felt, to protect it during the brutal processing ahead. This protective layer prevents the fresh wool from tearing or developing weak spots, as it receives thousands of impacts. The roll is then lashed to a rope and dragged behind a horse across the steppe for miles. Sometimes the roll is pulled behind a galloping horse for maximum impact force. At other times, children and adults take turns dragging the bundle over rough ground, singing rhythmic work songs to coordinate their efforts. The pounding compresses the wool, forces the microscopic scales to catch and interlock, and generates enough friction heat to further activate the felting process. After hours of dragging, the roll is unbound. The wool has transformed from loose fiber into a dense, unified textile, but the process is not finished. The felt is rolled again from a different angle and dragged further to ensure even compression and eliminate weak spots. A single piece of finished felt may be dragged 10 to 15 kilometers over the course of 2 days. The final product is a thick, heavy sheet. Sometimes 4 or 5 centimeters deep, it can be cut and shaped to fit the jair's frame. Multiple layers of this felt cover the structure, with the thickest pieces reserved for the northern wall, where wind pressure is greatest, and the southern opening, where heat escapes most easily. The thickness is substantial, but felt does not merely block cold. It actively generates heat. Wool is hygroscopic. It absorbs moisture from the air. The interior of a jair is humid from the breath of sleepers and the steam of boiling tea. As dry felt walls absorb this moisture, hydrogen bonds form between water molecules and the wool's amino acids. This bonding is exothermic. It releases heat. Research shows that 1 kilogram of dry wool can release approximately 100 watts of thermal energy for several hours while absorbing moisture. This means that as the temperature drops at night and the relative humidity inside rises, the walls chemically generate heat. The felt acts as a thermal battery, buffering interior temperature against the external freeze. Modern insulation fails in the jair context because it is impermeable. Fiberglass and foam trap moisture, which condenses and freezes into an ice shell that destroys thermal resistance. Felt breathes. It allows moisture to migrate through the wall and sublimate on the outside, keeping the insulation dry and functional. This hydrological management is as critical as thermal resistance. Insulation without heat is a cold box. In a landscape with no trees to burn, the Mongols harvest the only abundant energy source, the solar energy their herds process into dung. Wood burning is reserved for structural frames, not fuel. Instead, herders collect and dry animal waste. Argol, cattle dung, dries quickly and burns fast with high flame. It serves as summer fuel for rapidly boiling water, but provides poor sustained heating. Kurgan, a compacted mixture of sheep and goat dung, serves as winter fuel. In winter pens, sheep trample their droppings into hard layers mixed with urine and earth. Herders cut this compacted floor into dense blocks. These blocks have an energy density of 14 to 16 megajoules per kilogram, comparable to lignite coal. They burn with slow, smoldering intensity, providing steady, radiant heat that endures through long winter nights without frequent refueling. The stove sits in the exact geometric center of the GR. This placement is not a cultural preference. It is a thermodynamic optimization. The stove itself is typically cast iron, squat, and cylindrical, with a flat cooking surface on top and a firebox below. In recent generations, steel oil drums have been repurposed as makeshift stoves, cut and welded to create efficient combustion chambers. The door of the firebox faces the entrance of the jair, allowing easy fuel loading without crossing the sacred space near the altar. The stovepipe extends straight up through the tonneau. The temperature differential between the fire, approximately 600 degrees Celsius inside the combustion chamber, and the outside air at -50 creates a massive draft. This stack effect is the engine that drives the entire heating system. Fresh oxygen pulls in through gaps around the door and through deliberate ventilation slots left between felt layers. Smoke expels efficiently through the tonneau, which can be partially closed with a felt flap during the worst storms to prevent heat loss while maintaining enough draft to keep combustion active. This natural draft eliminates the need for mechanical fans or bellows. The fire regulates itself. If combustion slows, less hot air rises, reducing the draft and allowing more oxygen-rich cold air to enter from below, accelerating combustion again. The system is self-balancing. Heat radiating from the central stove strikes the conical roof and rolls down the curved walls, creating natural convection loops that circulate warm air to the perimeter sleeping areas. The circular shape prevents cold corners where stagnant air could accumulate and freeze. Every square meter of interior space receives thermal circulation. The sleeping platforms are arranged around the perimeter, raised slightly off the ground on wooden frames to avoid the coldest air layer that settles at floor level. During deep winter, the stove burns continuously. Someone must wake every 2 to 3 hours throughout the night to add fuel. Families develop sleep rotation schedules. The eldest child often takes the midnight watch, learning responsibility and fire management skills that will be essential for their own future household. Letting the fire die completely is dangerous. Restarting combustion from cold embers when the interior temperature has dropped below freezing can take an hour or more. During this time, cold seeps through the felt, and fingers become too numb to handle kindling effectively. The GR does not fight thermodynamics. It orchestrates them with precision that rivals engineered heating systems. The jair provides the microclimate. The human body must adapt to survive inside it. This adaptation is dietary and metabolic. The summer diet consists almost entirely of dairy, fermented mare's milk, yogurt, and dried curds. This is tsagani day, white food, which cleanses the system during months of surplus milk production. Winter demands ulani day, red food, meat. The caloric intake of a winter herder exceeds 3,000 to 4,000 kilocalories per day. The diet is heavy in animal fats and proteins from mutton, beef, and horse. Digesting these dense macronutrients triggers dietary thermogenesis, a process where the body generates significant internal heat simply by breaking down food. The nomads stoke their metabolic fires to match the stove. To overcome the logistical challenge of transporting meat over vast distances, the Mongols air-dried and pulverized it into yurts. This lightweight powder preserves for years and reconstitutes instantly into high-energy soup. This field ration enabled Mongol armies to travel without supply trains. It remains a survival staple. Clothing provides additional thermal layers through strategic air trapping. The deal, a long, tunic-like coat, wraps around the body and is secured with a silk or cotton sash, tightly wound around the waist. This sash creates a sealed pocket in the chest area, trapping warm air directly against vital organs, heart and lungs. The pocket acts as wearable insulation. Winter deals are lined with sheepskin, fur facing inward to trap air against the body. Wolf fur is particularly prized for hat ruffs because it does not accumulate frost from breath as easily as other furs, keeping the face protected without ice buildup. Mongol boots feature distinctively upturned toes. The cultural explanation involves avoiding disturbing earth spirits. The thermodynamic reality is that this design creates an air gap in front of the toes. In the saddle, feet are immobile and vulnerable to frostbite. The air pocket insulates toes from freezing leather and metal stirrups. Every element integrates: shelter, fuel, diet, clothing, all calibrated to the same environmental pressure. The jair is also an instrument of time. The orientation is fixed. The door must always face south. This is not superstition. A south orientation shields the opening from the fierce north and northwest winds that dominate the steppe winter, protecting the interior from drafts and snowdrifts. But the south-facing door does more. It turns the entire structure into a solar chronometer. As the sun crosses the sky, the ray of light entering through the tonneau travels around the interior lattice wall at a predictable rate. The Mongols divided the day into 12 zodiac animal hours, not Western clock hours. Snake hour runs from 9 to 11 in the morning. The sun hits the western wall section. Horse hour spans 11 to 1. The sun reaches zenith at noon. Monkey hour covers 3 to 5 in the afternoon. The sun strikes the eastern bed. The family synchronizes labor with the moving. Sunbeam, milking, grazing, cooking. No mechanical watch is needed. The house itself is the clock. Interior space is hierarchically organized to prevent conflict during months of confinement. The area opposite the door, the hoymor, is the place of honor. It houses the family altar and photos of ancestors. Elders and guests sit here. It is also the warmest spot, furthest from the door draft. The west side is a male domain. Hunting gear, saddles, and bags of fermented mare's milk occupy this space. The east side is a female domain. Kitchen tools and children's items rest here. The hearth belongs to the fire spirit, Gal Golomt. Throwing trash or water into the fire insults the provider of warmth and life. Stepping over the stove violates its sanctity. These rituals reinforce the survival systems. The fire must be respected. Without it, the jair is just a cold felt box. The most sophisticated feature of the jair is not its construction. It is its impermanence. In a landscape subject to catastrophic disasters that can kill 90% of livestock if trapped in the wrong location, mobility is the only real security. When pastures fail due to drought or desude, herders engage in odor, a strategic retreat to reserve pastures, often hundreds of kilometers away. The jair's portability allows the human shelter to follow the energy source, the livestock, rather than forcing animals to graze near a fixed building. This is the fundamental adaptation that enables human life on the steppe. The ability to pack up and abandon a dead pasture is survival itself. Static houses become tombs. The jair acts as an escape pod. Modular design allows individual repairs. If a roof pole snaps in a storm, it can be replaced without dismantling the structure. If a section of felt rots, it can be swapped. The system is redundant and resilient, capable of functioning even when partially damaged. This philosophy of mobility is now being tested in a new context. Mass migration to the capital, Ulaanbaatar, has created vast jair districts, static shanty towns where hundreds of thousands of former herders live in yurts fixed in one place. The jair was designed to sit on open earth and move frequently. When fixed in a city, the soil beneath it freezes permanently, causing heat loss into the ground. On the open steppe, smoke from dung fires disperses instantly. In the valley of Ulaanbaatar, using raw coal instead of dung, The gyrs contribute to some of the worst air pollution on the planet. The design features that trap heat now trap toxic particulates. The airtight felt and low ventilation are harmful in this context. Removing mobility breaks the integrated system. The shelter that evolved to survive the steppe cannot survive stasis. The Mongolian jair is not a relic. It is a highly optimized solution to a specific set of thermodynamic and logistical constraints. Wind dictated the circular shape. Cold dictated the wool chemistry. The herd dictated the fuel. Disaster dictated the mobility. From the microscopic scales of wool fiber to the daily rotation of the sun through the tunnel, the jair integrates multiple systems into a seamless survival machine. At -50 Celsius, when modern infrastructure cracks and fails, the jair functions perfectly. 3 millennia of refinement produced a structure that strengthens under snow load, generates heat through chemical reactions in its walls, measures time through solar movement, and can be dismantled and moved in under an hour. The circle of felt and wood creates a tropical microclimate in the heart of a frozen desert. The jair proves that human ingenuity, when aligned with the laws of nature rather than fighting them, can endure conditions that seem designed to extinguish life. It functions as an instrument of survival, tuned to the wind's frequency.